Hello everyone, I am Dr. Shalini Hanok, Assistant Professor in Department of Electronics and Communication, ATME CE, Mysore. Today I will be discussing experiment in communication lab, that is part B experiment, simulation, experiment using Simulink. Experiment number 1 is simulate NRZ RZ half sinusoid and generate eye diagram for polar signaling. Before going to the experiment, let me introduce you about the basic concepts of it. Let us see there are the different techniques involved in digital to digital conversion. We have analog to digital conversion and digital to analog conversion. Similarly, we have digital to digital conversion also. In this experiment, we will see how we can represent a digital data by using a digital signals. There are different techniques used for digital conversion signals, that is line coding, block coding and scrambling. Usually we represent all the digital signal converted to digital data into digital signals into line codes. Let me introduce you what exactly line coding and decoding is. Line coding is a process of converting the digital data to a digital signals. The digital data can be in the form of text, numbers, graphical images, audio or video, anything which is stored on computer memory. Line coding converts a sequence of bits into a digital signal. At the receiver, the digital data are recreated by decoding the digital signals back to digital format. There are different number of applications of using line codes based on the advantages it has. The main advantages of your line codes are: it minimizes the transmission hardware, it has easy error correction and detection, and facilitates synchronization and eliminates DC component. Since it has all these advantages, it can be used in number of applications such as transmission lines for transferring the data, infrared remote controls, free space optical communication, and it can also can be used as to create the barcodes, magnetized ports on the hard drive or tape drive, bits on an optical disc, and there are many number of applications using the line codes. There are different line code schemes which have been developed for converting a data into a digital signal. These are the different schemes: unipolar, polar, bipolar, multi-level and multi-transition. Unipolar, bipolar, all these things require formatting, the way it can be coded, that is NRZ coding and RZ coding. NRZ line coding is a binary code in which ones and zeros are usually represented by significant conditions such as plus V or and minus V. It has two different states, that is plus V or it has minus V. And in this NRZ format, we don't have any data which is coming back to 0. It has only higher level or negative levels. So it is called as non-return to 0. In return to 0, it describes the line code which can be used in a transmission signal, in which the data, in between the data, it returns back to 0. Whether it is 1 or 0, finally the data is returning back to 0. That is the reason it is called as return to 0. These two format of data is used in different coding schemes like unipolar, bipolar and polar and all. For our experiment, for the syllabus, we have polar NRZ signaling. This is how a polar NRZ signaling looks like, wherein we have a data bit. Here the input data bit, this is converted into a polar NRZ format, wherein when the data is 1, the signal will be of plus V volts. It can be any voltage, it can be 1, 2, 3 or any voltage. So it is higher than 1, some voltage, positive voltage. And when the signal is 0, the data is going to negative level, negative voltage level. It can be any negative level. So now we can see same thing. Wherever 1 is there, we have higher voltage level. Whenever 0 is there, it is into lower voltage level. This is how a polar NRZ signaling looks like. Then we have a polar RZ signaling, that is return to 0. So here this is again a data bits which is in the receiver end, and this is the polar RZ conversion of it, where whenever the signal is 1, the data, half the data will be high value and half the data will be 0 value. Here in 1 only, in between of the 1, the data is going to 0, that is it is returning to 0. Then in 0 bit, the level is lower, negative level, that is negative voltage, and in between the 0 it is coming back to 0 bit. So half of the signal will be negative voltage, half of the signal will be 0, returning to 0. Same thing continues again for 1, half of the signal will be positive voltage and half of the signal will be 0, and it goes on. This is how a polar NRZ and polar NRZ RZ signal looks like. Now we will go into the implementation part, how these signals are implemented in Simulink. This is the circuit diagram for polar NRZ, and we are going to represent it in scope also and also in the eye diagram. So we have this Bernoulli's binary generator, it generates the signal. Then we have these constants to give positive and negative voltage peaks. Then finally we have a switch which switches between the positive voltage and negative voltage. Finally we can display it. Now we'll see this practically how this works. We are doing all these things in MATLAB Simulink. Let us open MATLAB. Okay, this is MATLAB, and here is the icon to open Simulink. Simulink is basically a drag and drop tool wherein we have different libraries, various libraries wherein you have different models where you can drag that model and drop it in your project and create a project. This is how the library browser looks like. So before starting, we are going to create a folder wherein we will be saving our program. This is a library, Simulink library, from where we are going to drag and drop the models, whichever model we want. So here is a new, so we want a new file, new model to be designed in that particular file. So this is a new file. Place it next to each other so that it will be easier for us to drag and drop the models. Initially we will be doing the NRZ model. Okay, let me start with the first experiment, that is NRZ model. In this particular section, in this particular space, we are going to search for the model which we want. So as I showed you the diagram of NRZ polar signaling diagram, we initially need some model which generates the binary data, Here we have Bernoulli's binary data that we are going to search in the section here. Okay, now we have a Bernoulli's binary generator which is here. Drag that and drop in your workspace. Then we need two constant blocks wherein we can declare whatever constant value we want, positive voltage and negative voltage and all. So we have a block something called as constant. So here is the constant block. We need two blocks for positive voltage level and negative voltage level. Then we have to switch between this positive voltage level and negative voltage level, so we need a switch. This is a switch which switches between the positive voltage level and negative voltage level. Then to view all these we need scope, oscilloscope. So we are going to search scope also. So we drag and drop it. So for visualization, let us increase the model. Okay. Now the diagrams, the models are ready for connection. We have placed it, dragged and dropped it. Okay. Now we have a connection from Bernoulli's binary data. We'll connect it to the switch. So we will make sure whenever there is a connection, it should be in black, that line will be in black in color. So if there is no connection, the line looks like this. It will be red in color. If it is red in color, it means there is no connection. So we should make sure there is a connection. So we are going to connect one constant here because two thresholds we are giving. Okay. We can label it if you want. This is the switch for NRZ signaling. This is positive voltage. This is negative voltage. We have the scope. Okay, this is the connection made. Now for scope we want both inputs and outputs to be displayed on the scope. So we are going to select the scope parameters and select two axes. For one is for input and one is for output. Here we will double click on the scope, then we'll go to the this scope window, and here you have something called as parameters, wherein you have all these number of axes, time range and all this. So since we want one for input and one for output, select number of axes as 2. Here time range, we can give this is x-axis time range what we want. So it's good if you give 20 so that we can see how many more number of signals, how much ever we want. Okay, and then give apply. Now we can see for 2 axes 2 graphs are created. Okay, now we will close this. Now we are going to give input at this end from Bernoulli's binary generator. Then we are going to give output from the switch. Okay, now to view the NRZ data generated, a model is ready. Now we have to set some parameters so that the model understands the operation. For that we will check the probability bit error. It's fine if it is 0.5, and here we have to give voltages. It's already set to 1 plus 1, so either we can leave it to 1 or we can set the voltage whichever level we want it to be. So it can be more than 0 anything, positive, 1, 2, 3 anything. So I will set it as 2 so that I can view it little clearly. So it is plus 2 and OK. Now this is here, it is by default it is set to 1, but here we have to give the negative voltage levels. Okay, remember we have to give negative voltage level. I put minus, and whichever signal number, the voltage amplitude we have given here, the same thing it's better we give here also, so that we can view negative and positive levels equally there, and press OK. Okay, now the voltage levels are given, Bernoulli's generator also is given. Now in switch we are going to check certain parameters. Here the threshold is 0, that is fine. Here the threshold, if it is more than, it should not be equal to, more than or equal to. So if the data which is coming from here, from the inputs, if the data is more than 0, then my switch has to go high and low. So the threshold is 0, it should not be greater than or equal to, it should be only greater than. So select U2 greater than threshold and press OK. Now all the parameters in all the models have been set. Now we have to view the output. So here is this icon where it says start simulation. So once we click that, our model will be simulated and we will get the output. Okay, now here it is the simulation time, stop time. So how much ever we want. If it is set to 10, then we will be getting the datas only till time duration 0 to 10. If you set it for more, then we will get more. So we can either set 10, 100, 1000, that. So let us set it for 100 so that we can see more number of signals. So between 1 to 100, how much ever we want, we can see. So now we will press start simulation. Now it is simulated. We will check the results in the graph. So now it is, see, now we can see 0 to 20 samples here. So this is the input from the Bernoulli's binary generator. We are having 1 0 1 1 0 1 1 1, right? The data continues, and accordingly there is a switching action here. See here, when it is more than 0, our voltage level is 2. Then when it is 0, our voltage level below 0, it is voltage level is -2. Then it is 1 here, so voltage level is -2 plus 2. Then again 1, then we have voltage level 2. So this is NRZ data which has been generated. Now we can label the axis also. So we can go to right click here, whichever axis labeling we want, go to axis property. So it is set to 5. We can even fix the amplitude levels also. Since my maximum voltage level is 2, I'll fix it to 3. And here labeling I can give, since it is an input signal, I will give it as binary data, binary data. Apply. Okay. Now we can see the maximum voltage level is 3 and minus 3 here, and my graph has been named as binary data. The same thing we can do it for output also. Access properties, here I'll give it as 3, 3. That can be left like that, it's okay. So here I will give this as NRZ signaling. Okay, so you can see the shift, and this is the NRZ signaling. I have labeled it. So time period I have given as 0 to 20. So how much ever you can give within 0 to 100, because here it is set to 100. Okay, that's how the NRZ data has been generated using the Simulink. Now I have not saved the file, I'll save it. I'll give save as. Go to file, save as, go to the folder, whichever folder you want to save the file, and I will name it as NRZ signaling, and by default it will be saved in the extension .mdl. If not, you can select it and save it. Now the file has been saved. Okay, now we are going to generate the eye diagram for it. How eye diagram will be generated? What is an eye diagram? I'll just brief you out what is the eye diagram. Eye diagram is mainly used to see the intersymbol interference of the signal. So it is for any signal. So we are going to check how much is the noise present in the signal and all that we can see using the eye diagram. For that, to see the eye diagram for NRZ signaling, as they have mentioned in the question for that in the syllabus, that generate the eye diagram for binary polar signaling. For this we will generate and see. To see eye diagram, we have to introduce the noise for particular NRZ data. So we are going to select something called as white noise, band limited white noise. So type the white noise here, you will get band limited white noise, and put that model here. Then we have to select add, so that we can add that particular noise to the NRZ data. Now we will do the connection. The models have been placed. Okay. So we are going to add the noise, this particular noise. Where we are going to add? We are going to add the noise to the NRZ signal which is generated here. Okay. Here is the noise NRZ data generated when we are adding the noise for it. Okay. Now we need eye diagram model to view the eye diagram. So click eye and select. We have this eye diagram block. So connect from here to here to see the eye diagram. Now the same eye diagram noise which has been introduced can also be seen on the scope. So we will select 3 probes, 3 axes, and for one we will give noise added diagram. How it will be, we will see. So So we can view the added noise in eye diagram also and also in the scope. Okay, now the connections are done. So now we have to set certain parameters so that the graphs and the signals are visible properly for our limit. So we will go to band limited white noise, and here the noise power is too high, so we cannot see the signals within the boundary which we have. So we will reduce the voice noise. So put it to 0.0001. Okay, now add is a block which adds the noise, and now in eye diagram we have to make some changes. So sample per symbol is 8, yeah, leave it that, and we have symbols per trace. One, just leave that, and trace displayed, and this is fine. Okay, now the model is ready for simulation. Let me simulate using this start simulation button. Okay, here is the eye diagram which is being generated. Okay, we can see the eye diagram which has been generated. This is how the eye diagram looks, and all these things are noise which has been added to the eye diagram. Okay, now we will see the same thing in the scope. Okay, see, we can clearly see here. So this is the binary data, this is the NRZ signaling which we have got, and here the noise which is been introduced. This we can label it as same thing as we did for previous. This is NRZ with noise. Okay, we can see this. See, here there is no noise, here there is noise, here there is noise. So in we have generated the eye diagram also. We have seen the noise introduced in NRZ signaling. This is the simulation for NRZ signaling. Okay, now we will see RZ signaling. We'll be saving the project. Now we will open a new project. This project is RZ. We are saving it. RZ signaling .mdl file. Save it. Okay. Now we are going to drag and drop our models. RZ is similar to NRZ. Here certain blocks we are going to add extra. We need Bernoullis block, drag and drop it. Then we need constant block, same as NRZ. 2 constant blocks, drag and drop it. Then we have switch block. Here, drag and drop it. Then to see the output we have scope. You have to type in a proper spelling here so that we will get the models. Spelling is wrong, then we will not get the models. Okay, now we will little maximize the block so that it's easy for us to view. Now this is for positive voltage, this is for negative voltage, this is a switching auction for RZ data signaling. This is to see the, now we will do the connection almost same as NRZ. Bernoulli's data will go here, then here we have two voltages given, now see it is red color, so the connection is not made, it should be black. Okay, now we are going to set the data same as what we did for NRZ. Okay, scope we will take 2 axes. We will set this range to 20. Okay, now we have set the axis. Okay, now one is going to the input, one is going to the output. Okay. Now this is for a diagram for NRZ. So for this we are going to add 2 blocks which will make the data RZ. So here, since we have to make the positive half of the cycle as higher voltage, then half of the cycle should go return back to 0, we will be using 2 new blocks, that is a product block and a pulse generator. Okay, these 2 blocks are added to this so that we will half of the cycle we will reduce back, bring back the signal to 0. From pulse generator we will connect to the product block. Then from this, the whatever the NRZ data we will be getting, we will be connecting to the product block. Okay. Now, okay. Now we will see the NRZ data also, parallelly the RZ data also. So we will just take one more probe, one more axis, so that NRZ and RZ can be viewed, so we can make out easily. We have this red line where connection is not established. We will establish the connection. Okay, now our circuit is ready for now the circuit is ready with the connections. Now we have to set some parameter as we did for NRZ signaling. Now in pulse generator, the duration, how much we need, that we have to set. Go to period, set it as 1, and amplitude should be 1, that is fine. Pulse width, how much width we need, how much duration the pulse should be in on condition, that is higher voltage condition for an NRZ data, that we can fix here. So 5, if we take only 5%, it will be on and then it will return to 0. So now let me take 50%, then it will return back to 0. This decides the width of your pulse. Then click OK. All things are set, and this should be in use simulation time mode and time based mode. OK. nothing to set in product, it will just multiply and give. Now the model is ready for simulation. Go to start simulation. Before that you can give 100 so that more number of samples gets simulated. Start simulation. So now we can view the output here. Okay, there is some problem in the output. Okay, there was a problem in the graph because I haven't set the threshold here. It was greater than or equal to, so set it to greater than and threshold would be 0. Okay, now the model is ready for simulation. Now we will simulate. Okay, now we can see the output here. It's nice. See here, again I can label the axis here. This is what maximum amplitude is 2 mine, so I am giving 3 maximum. So this is input, this is the NRZ data, NRZ signaling. Okay, now this is the RZ signaling. Okay, you can see here. So this is the input data and NRZ data I have explained. Now see here, whenever the from here till here it is 1 pulse, and for this half of the pulses, 50% of the pulses on, that is higher voltage, then 50% of the half of the data is returning to 0. See here. Then again, for again 1, from here to here 1 more 1, then we have half of the data is 1, half of the data is returning to 0. Same thing here, half of the data 1, half of the data 2. For negative is negative part, half of the negative pulse will be -2, half of the negative pulse will be 0. Same thing continues. This is how we will get input data, NRZ signaling, RZ signaling. Okay, so we have done with NRZ signaling with eye diagram also, without eye diagrams also, then RZ signaling. Now the last experiment in this we will be doing is half sinusoidal. Half sinusoidal generation is nothing but it is something like half wave rectifier. So we are going to give input as full sine wave, but we have to get a half sine wave. So let me save the file first. Go to desktop folder, and it is half sine wave. Save it. Okay, now before starting we need sine wave to be given as an input. Go to sine. See, we got sine wave generator here. Go to sine, take that and drag and drop it. Then we want constant to fix the level. Above 0 we want the wave, and below 0 we don't want the wave, so we want the constant. Then we want a switch to switch between the waves, so switch. So drag and drop it. Then finally we need a scope. This is a simple diagram, simple blocks, very easy to simulate. Then we have, so we don't have many blocks, we have only 4 blocks. Now let me magnify it for you. So that it can be viewed properly. Okay, now from sine wave we are giving the sine wave as an input here to the switch. We have to switch between the voltages here. Positive and half, negative half should not come and positive half should come, and we will be giving two inputs from the same sine wave. From same sine wave generator we will be giving two inputs. Then we have to give the levels, right? So we are going to give the levels from the constant. So we are going to fix the level as 0. If it is more than 0, above 0, we will get the wave. If it is below 0, we will not get the signal. So we will be, this is constant, we have to fix 0. Okay, now we have to set the threshold in switch. So it should be greater than threshold. If it is greater than 0 threshold, then we will get a sine wave. Then if it is below, we will not get. So finally, scope. Again we have to go to scope, select how much our parameter we want, that is axis. We will see both input and output. 2 is enough, so give the time period as 20. Okay, fine. Our parameters are set. Now we have to give one line to input. So one is given to the output of the switch. Okay, now the diagram is done. We will just label it if you want. This is for half sinusoidal wave, and this is the threshold. Okay, now our model is ready for simulation. We will start simulating. Okay, we have to set the parameters before that. Now go to the sine wave part. So here you have to follow these parameter setting so that we will get the wave properly. We have to, this is not time based, we have to go for sample based because we are taking each sample. Then this will be in use simulation time. Then samples per second. We will see more number of samples. If 10, only 10 will be given, so let us see more number of samples which is generated. So let me give 100 here. Then sample time, so let me make it small, I mean as small as possible, 0.01, so that we will get each samples properly, sampling it out. So these are the parameters to be set. Okay, then please press OK. Then constant, anyway I have set it to 0, which has to be 0. Then switching threshold, as I told you, it is 0 here and it is greater than threshold here. Okay, now the model is ready for simulation. So we will again use 100 here so that more number of samples get simulated. Start simulation. Now it is simulated. Let me see the output here. Yeah, fine, we have a very good simulation scene here. See here, again I'll just set this axis property to 3 so that it will be viewed really nicely. So this is this sine wave which is being full sine wave. Let me give the name as full sine wave. Okay, done. So see, now we can see it clearly. Okay, same thing we'll do this for this also. Axis properties 3. Okay, half sinusoidal wave. Okay, see, now we can. So if we still want to amplify and see, we can set here as because maximum amplitude is 1, let me set it to 2 so that it can be viewed still more bigger. Okay, now we can see. Oh, my scales are changed. I clicked it. Oh, yeah, now it is. Okay, just scale is shifting, that's it. So here we have a sinusoidal wave. We can again go back anyways and set the properties here, apply. It is zoomed a lot now. Okay, apply. Okay, now we can see here, so it has been labeled, and this is a sine wave. We are getting half sine wave, half works as an half wave rectifier. That's it. That's about this this program, this experiment where we have generated half sinusoidal wave. So that is the end of this first experiment, where it says this is the models. So according to first experiment, we have simulate NRZ RZ half sinusoidal and generate I diagram for polar signaling, which we have done for NRZ. So that's it about the first experiment. Thank you all. Thank you one and all for listening to this video. Thank you.